Hey, Gabriel, we're back.
We're back for
And it's
episode
2 of April.
of April.
So you promised and you delivered as
delivered.
well. I never do that. Well, that's okay. So who did you find this time?
So we talked to Adrian Tsai. He's
Okay.
a developer over in OSG, Operating Systems Group.
In DirectX.
Yeah, in DirectX.
Okay.
And a couple weeks ago, he gave a presentation of the stuff that you're about to see in today's episode of GoingNative to some MVPs. And I was told the presentation went really well. And after watching him, I believe it.
Okay,
So-
cool. Is it kind of, you were saying it's kind of long, but it's very engaging.
Yeah. So if you look at the counter, you'll see this episode's a bit longer than other episodes, but I promise you that you will find it very valuable, very engaging. Adrian is a great presenter, and talks about some stuff with graphics, which I think, for a lot of people, when they hear graphics, it's shaders and vectors and vertices and all that thing is very complicated, and he leaves just the right amount of detail in and the right amount of detail out. And I think you guys
You
will
got me there. Let's go. Let's go watch it. Cool.
Hello, everyone. Welcome to our latest episode for Channel 9 GoingNative. My name is Gabriel Ha. I am here with Adrian Tsai. Adrian, go ahead and just tell us a little bit about yourself and what we'll be talking about.
Well, my name's Adrian. I'm a developer on the graphics tools team, Operating Systems Group. I've been at Microsoft for about 2 years now. Started on Windows Phone, now on graphics tools and operating systems. And on the graphics tools team, we build tools, funnily enough, for developing and debugging graphics in DirectX applications. And specifically, the feature that I worked on was offline analysis, and that's what I'll be talking about today.
Let's get to it.
Yep. So offline analysis is one of the new graphics tooling features that'll be appearing in Visual Studio 2013 Update 2. I think, technically speaking, in Visual Studio it's actually called graphics frame analysis, but I call it offline analysis because it's shorter. And so before I start, and I should probably warn that the content I'll be going through is fairly technical. It's going to involve a lot of deep analysis, and we're going to delve a little bit into GPU performance. So even though that's the case, I'm going to try and keep it accessible, even for people who aren't experts in GPU performance. So you might see me gloss over a couple of details here and there, but I'm assuming that most people have already got a basic understanding of how GPUs work in general. So I think it might be useful to go through a sort of brief introduction of graphics diagnostics and offline analysis first. So if you've ever tried developing a game or something like that, you know that typically trying to debug the rendering of your application can be a real pain if you don't have any tooling. Often you have problems like, oh, my object is rendering black, or nothing is showing up in my scene, I don't know what's going on. And to debug that, you want to be able to look at things like D3D state and your pipeline objects and your pixel history and that sort of thing. And the way we debug these sorts of things is via something that we call capture and replay. So what this means is that you launch your app or your game under a tool which will record every single D3D API call that you make and all of the parameters as well, and will stream everything out to a file. And then later on, using Visual Studio, you can crack open this trace. And what it'll do is it'll replay every single one of these logged API calls exactly as you made them, and then we can reconstruct your frame draw by draw, API call by API call. And this is what exists in Visual Studio 2013 today. You can take a trace, you can crack it open, you can look at all the D3D API calls that your frame made, you can replay the rendering and step through it, and this is what allows you to look at things like pipeline views and pixel history and your resource contents and events lists and all the rest of that sort of stuff. And so that's just what graphics diagnostics looks like in Visual Studio 2013 today. You have your events list, you have your graphics pipeline stages, your D3D object tables, your pixel history, and your render target contents and all the rest of that stuff. But once we have this trace, we can do all sorts of other interesting things with it. Not that debugging isn't interesting, but I mean interesting performance things. Something really simple we can do is, while we're playing back all of these logged API calls, we can just insert D3D timing queries in between every single draw call, and that will allow us to tell how long every single draw call took to execute on the GPU. And even that in itself is pretty useful. It's the ability to tell how much GPU time was spent on each draw call just using the trace. You don't have to modify your source code. Using the trace, we can insert these timestamp queries for you. But there's also other things that we can do to gain sort of deeper insights into the performance of your application. and even independent of what hardware you're running on. For example, we can modify parts of the D3D state while we're playing back. For example, we could turn on multi-sample anti-aliasing, or we could turn on anisotropic filtering. You could halve all of your texture sizes, and then we can remeasure the time taken for every single one of your draw calls. So this allows us to tell you things like, this is how long the draw call took with just the defaults when we didn't change anything. This is how long the draw call took when we turned on 4 times MSAA. This is how long the draw call took when we halved all of your texture sizes and things like that. And you can use this information to deduce some pretty deep things about the rendering in your application. And this is essentially what offline analysis does. You know, it's a feature that takes a graphics diagnostics trace and will automatically play it back multiple times. And each time we play it back, we change some aspect of the rendering to show the impact on the performance of that change. And using the information provided by offline analysis, you can actually infer a pretty surprising amount about what the GPU is doing under the hood. So that was a kind of 30,000-foot overview of graphics diagnostics and offline analysis. So I think I'd like to jump straight into how do you actually use this feature? How would you, if I'm a third-party developer with an application with a performance problem, how would I use offline analysis to improve the performance? So I wrote a very simple application. And I just did this in my spare time. It's a pretty basic app. It draws the Earth, it draws a skybox, it draws the sun, and the Earth has all of the usual trimmings. It has a diffuse map, it has per pixel specular lighting, it has a normal map, it has a cloud map and a specular map. On the dark side of the planet, we have a night map for the city lights. We draw the Earth's atmosphere using a Vertex shader, and we solve the light scattering equations per vertex. We have all of the usual post-processing effects. You know, we have bloom and we have glare and we have HDR and tone mapping and all the rest of it. And you can kind of play around with it and watch the white balance adjust and all the rest of it. So pretty basic application. But it doesn't just run on Windows, of course. It also runs on phone. So here I have my obviously not production engineering device, and I have the exact same application running on the phone. And if I launch it, you know, you see that exactly the same thing. You know, I can pinch to zoom, I can scroll around, and it's the exact same code, exact same application running on both desktop and phone. So that's our sample application. So I don't know if anybody noticed, but when it was running on the phone, the frame rate is not great. So ideally, we want to be running at least 30 frames per second or 33 milliseconds per frame. And right now, on this device, which is a Qualcomm Snapdragon 800, which is an extremely powerful chipset, mind you, it's taking about 50 milliseconds per frame, or 20 FPS at its native resolution of 1280 by 720. And this means that we need to shave at least 17 milliseconds off our render time to hit our target of 30 FPS. And I'll be using Windows Phone for this entire demo. All of the traces and all of the reports that I gathered that you'll see in a moment, they were all gathered using Windows Phone, using this device here, in fact. It runs exactly the same on the desktop. It's just that when I ran the sample app on my workstation in my office, it was running like 300 FPS or something like that. And optimization of an application running at 300 FPS seemed a little bit silly. So I'm using a phone primarily because these are the kinds of devices where you're more likely to have these sorts of performance issues. And as a sort of bonus, we will get to see some cool hardware GPU counters that Qualcomm have provided us as well, which will come in handy later. And as much as I wanted to do a real-time demo, you know, live using Visual Studio, it was just kind of impractical given how much content I'll be going through today. So I just used offline analysis in Visual Studio, generated a whole bunch of traces, and just copy-pasted screenshots into my slides. But trust me, when you actually get Visual Studio Update 2, you can actually run it, and you can actually get the exact same results. I've just pasted screenshots into my slides to save some time. So first things first. I'm not even going to look at performance yet, because there's just something wrong about it that needs to be fixed first. And it's probably impossible to spot on a static image like that. So the actual problem is that the textures look pretty bad from a distance, and it gets a lot worse in motion. There's a lot of aliasing in the Earth's texture maps, and before looking at performance, there's just something that should be fixed. There are a couple of things that can cause this, really. You might have messed up your sampler state, or maybe you forgot to turn on bitmaps, or maybe you've got something strange going on in your pixel shader that's causing this. Obviously, if you had your trace open in Visual Studio, you'd just use regular graphics diagnostics to debug this info and to look at your pixel history and your pipeline state and all the rest of it to find out what's going on here. But I don't have Visual Studio installed on this machine, but I do have an analysis report on hand, and I'll use that to deduce what's going on. So to get this from Visual Studio, when you have a trace open, a VSG log open in Visual Studio, there's a tab that says Frame Analysis, and you click that tab and click the button, and it'll run the analysis, and it'll give you a report that looks very similar to this. So over here, the bar chart at the top here is, it contains the relative time taken for each draw call in the trace. And a taller bar means that that draw call took longer. So you can see at a glance that this draw call took the longest, because obviously it has the longest bar. And each of these draw calls corresponds to one of the rows in this gigantic table of percentages down here. I've also annotated my application with D3D perf marker events. And that allows us to easily see which draw call is what. And you can either use the D3D perf API or the ID3D user-defined annotation API, and you can mark out sections of your rendering. And then when you do that and you capture your application and you run it through offline analysis, they'll just automatically show up, and you don't need to do anything. And it'll aid helpfully in figuring out what parts of your scene are actually rendering what. So you can see the most expensive draw call is this one, the one that's taking 11.66 milliseconds, and we can see from the perf marker that this one is drawing the Earth. Now on the left side column here are the baseline values, and these are the timing values for each draw call when we didn't change anything, right? So it's just measuring the GPU time taken to execute every single draw call as it came from the trace. But we also run experiments, which means that we change some aspect of the playback and we remeasure how long it took for every single draw call. So most of the experiments are pretty self-explanatory. For example, setting a 1x1 viewport, or we can force point texture filtering on all of your samplers, or we can, generate bitmaps for every single one of your textures, and then we remeasure the time taken for every single draw call, gather it all up, and then present it in this giant table of relative values from the baseline. So because these values are relative, a value of 100% means that there was no change relative to the baseline. A value less than 100% means that it was faster than the baseline. A value greater than 100% means that it was slower. So for example, in this column, this draw call here, so what this is telling us is that when we're drawing the Earth and we forced point texture filtering on, this draw call got 18% faster because it's 82% of the baseline. And if you look over here, in this column, there is a bit of green here. And what this experiment does is that whenever you create a texture, if you're not already using a full MIP chain, we will automatically create a full MIP chain for you. And so you can see that in the MIP generation experiment, when MIP maps are turned on, there was a significant effect in performance, almost 3x faster. Now, so we can just use this to kind of tell that we don't already have MIP maps on, because obviously if MIP maps were already on, turning on MIP maps wouldn't have changed anything, and this value would be 100%. But because this value is so significant, we can kind of just deduce that we forgot to turn on MIP maps for this draw call. And so, yeah, that's just a rookie mistake. We forgot to turn on MIP maps for this draw call, for this texture, and that's easy to fix. I mean, for an object in a 3D scene, you should usually be using MIP maps anyway. It's not even a performance thing, right? It's just a correctness issue. When your textures undergo minification, you don't want lots of aliasing artifacts like we were seeing before. And yes, one thing I should note is that the styling for this report is completely not final. It will look very different when you install the final RTM version of Update 2. I generated these reports using some random RC build I had installed on my dev machine, but don't panic if when you actually run this, the colors look a little bit different. The general layout will be exactly the same, it's just the styling and the coloring will be a little bit different in the final RTM version. So anyway, I went ahead, I turned on MIP maps, and I took another trace. And this is now what it looks like. So the one on the left is without MIP maps, and the one on the right is with MIP maps. And now there's a problem. The textures look too blurry. It went from having too much high-frequency information causing aliasing, now to not having enough so that it looks blurry. And every developer knows that in this circumstance, the quick and easy solution is just to turn on anisotropic filtering. But before we do that, let's just rerun offline analysis again with our latest changes and take a look at the report first. So you can see that the cost of drawing the Earth has dropped significantly, and that's this one over here. And you can tell because the relative cost of everything else went up. So that's what it was before, and that's what it is now. And obviously, because these times are relative, this bar got a lot shorter, so it looks like everything else went up. But we can see that drawing the Earth is still the most expensive draw call, taking 4 milliseconds just by itself. So just drawing the Earth is taking 4 milliseconds on the GPU. And we want to turn on anisotropic filtering. Well, what's that going to cost us? Recall that we have a performance goal of 33 milliseconds per frame in order to get 30 frames per second. And we're already past that budget. We don't want our textures to look terrible, but whether we can actually use anisotropic filtering or not depends on how much it costs. And I could do the traditional thing. I could, change my application and recompile it and see the impact of anisotropic filtering. But that's, if you're developing a game or something, that can be a real pain because you have to recompile, redeploy, restart the level, and probably play for another 15 minutes to get to the point where you're having the problem in the first place. But the benefit of offline analysis is that I can see right here that for this draw call, turning on anisotropic texture filtering would have a significant performance degradation. And this number, 230%, what that means is that when anisotropic filtering is turned on, this draw call took 2.3 times the time that the baseline took. So that would bring the time for this draw call up to about 9.2 milliseconds. So it took 4 milliseconds for the baseline. When we turn on anisotropic texture filtering, that's 230% of the baseline, brings it up to about 9.2 milliseconds. And if I had this open in Visual Studio, you can hover over any of the cells and it'll give you the detailed information. So the time went up from 4 milliseconds up to 9.2 milliseconds, which when we've got a budget of 33 milliseconds is kind of an expense that we can't afford, especially considering we're already over that budget. I think currently we're running at 37 point something milliseconds per frame on its own. As a quick aside, we can kind of tell that we're already using trilinear filtering. So we can tell that because this column is 100%, but when we forced on point texture filtering, we saw a small increase in performance. When we forced on bilinear texture filtering on all your texture samplers, we again saw a small increase in performance, and obviously when we turned on anisotropic filtering, there was a big performance drop. But there was no change when we set trilinear texture filtering. So that kind of tells us that we've already got trilinear texture filtering turned on, which I think kind of makes sense because I believe trilinear is the default D3D11 sampler state. So anyway, with the anisotropic filtering, so what's going on here? We don't expect anisotropic filtering to be free by any means, but 230% compared to trilinear, that's a lot. And it's just too high of a cost for us in our performance budget. And moreover, this is telling us that turning on anisotropic filtering is more than doubling the time taken for this draw call, which seems a little out of the ordinary, even for 16 times AF. I mean, if you're playing Crisis or something, you don't expect your frame rate to halve when you turn on 16 times AF. So it means that we must be bottlenecked by something here that's causing anisotropic filtering to be so extremely slow for this draw call. And we can get a better picture of what's going on by looking at GPU counters. So in addition to collecting timing data, we also collect GPU hardware counters for all experiments. And GPU hardware counters are IHV-defined hardware-specific counters returned by the GPU. And using these values, it's possible to get very deep hardware-specific information about your rendering. So what the analysis engine did is that it ran the baseline, which is without any changes, remember, and then we collected all of the timing data and all of the GPU counters for every draw call. And then we did the same thing for the 1x1 viewport experiment. We shrunk the viewport to 1x1. We collected all of the timing data, collected all of the GPU counter data for every draw call, and so on and so forth for every single experiment that we run. So let's take a look at the GPU counters that we collected when we were running the anisotropic texture filtering experiment. In other words, the GPU counters when we forced 16 times anisotropic filtering on every single texture sampler. There's the marker that's telling us that's the draw call that drew the Earth. And the first thing I notice is that the counter called texture fetch stall has a value of 169%. This is compared to the baseline, which is using trilinear, remember, where this value is only 37%. Now, what this counter actually means is that it's the ratio of time the GPU spent waiting on texture fetches versus doing actual work. And a value greater than 100%, as it is here, means that the GPU spent more time waiting on texture fetches to come across the bus than it did doing actual useful shader work. But regardless, even if you didn't happen to read the Qualcomm white paper and you didn't know exactly what the interpretation of this counter meant, the thing is called texture fetch stall, which has a value of 169%, which just sounds like a bad thing. So if we scroll down, we can also see that we're spending 99.7% of our time in the pixel shader, which kind of makes sense because that's where the vast majority of our workload is. But take a look at this one, the counter called texture memory read bandwidth. This has a value of 35, 36 megs just for this draw call. And what this means is that the GPU is reading 35 megabytes of texture data across the memory bus just for this draw call when anisotropic filtering is turned on. And this is in contrast to the baseline counters, where this counter only has a value of about 7 megs of texture data. So this is just kind of interesting to know that with trilinear filtering turned on, the GPU had to transfer 7 megabytes of texture data across the bus. With anisotropic texture filtering turned on, the GPU had to transfer 35 megs of data across the bus. So that's 5 times the memory bandwidth used just by turning on 16 times anisotropic filtering. Now, as a quick aside, the Qualcomm Snapdragon 800, which is what's inside this phone here, which is what I use to run all of these reports, it has an 800 megahertz memory bus connected to dual channel double data rate memory. This means that if we can transfer 4 bytes per cycle multiplied by 800 megahertz, multiplied by 2 if you can read from both memory channels simultaneously, multiplied by 2 for the double data rate, this equals 12,800 megabytes a second of peak theoretical bandwidth. Now, this draw call with anisotropic filtering enabled is transferring 35 megabytes of texture data across the bus. 35 megabytes divided by 12,800 megabytes a second is 2.7 milliseconds. So just transferring the texture data for this draw call across the bus took 2.7 milliseconds, assuming peak theoretical bandwidth, which we would probably never get in real life. And remember that the draw call itself only took like 9.2 milliseconds. So even if we assume that we are getting maximum peak theoretical bandwidth, almost a third of the time of this draw call is spent just waiting on data to come across the memory bus. And in real life, in practice, we're probably not going to get peak theoretical bandwidth. So in practice, it's probably a much larger proportion of this 9.2 milliseconds is spent just waiting on memory to come across the bus. So where are we with our analysis so far? Well, we've turned on bitmaps, but it looks terrible without anisotropic filtering. We want to turn on anisotropic filtering, but it's just too expensive. But by looking at the results from the anisotropic filtering experiment, we can now tell why. So the percentage of time shading pixels counter tells us that we're spending all of our time shading pixels. So that's where our workload is. And turning on anisotropic filtering causes the GPU to consume 5 times the memory bandwidth, and we can tell that by comparing the bandwidth numbers between the baseline, which is using trilinear, and bandwidth numbers from the anisotropic filtering experiment. The texture fetch stall counter tells us that we're stalling the GPU on texture fetches, and it's not being limited by ALU capacity or anything else. And we can deduce from the texture memory read bandwidth counter that we're just getting murdered by memory bandwidth limitations on this device. So the question is, what can we do about it? Let's just go back to the top of the report. This is the exact same report I was looking at just a second ago. I just jumped back to the top. And we can see that in addition to being really expensive to turn on anisotropic filtering, there is a little bit of green in this column over here, marked BC texture compression. It's not a big difference. This has a value of 93%, so it was only a 7% gain in performance. But remember that these numbers are relative to the baseline. The numbers we were just looking at, the ones where we found that we were memory bandwidth bound, those were when anisotropic filtering was turned on. So we already concluded earlier that the anisotropic texture filtering experiment caused us to be heavily memory bandwidth bound because obviously AF uses so much memory bandwidth. But that's not so much the case for the baseline, because the baseline is using trilinear, which doesn't have such heavy requirements on bandwidth. And we can tell that because even when we reduced the texture dimensions to quarter size, it didn't have that big of an impact on performance. But it's because this number is green here that we can tell that we're not already using BC texture compression, right? Because obviously, if your textures were already compressed, recompressing them into another compressed texture isn't going to make any difference in your performance. So we can tell that because there was an effect here, that we're not already using compressed textures. So this is where we are right now in our analysis. So we turned on bitmaps, which fixed the aliasing issues. But it looks terrible with trilinear filtering. we want to turn on anisotropic filtering, but we've shown that we're too constrained by memory bandwidth to do so. And we can see that we're not currently using BC texture compression. And so the obvious next step is to start using BC texture compression. We should recompress our textures from a 32-bit BGRA into a block compressed format. And it'll sacrifice a little bit of visual quality because the compression isn't free in terms of image quality, but it'll save us a huge amount of bandwidth. So I've done that. I've re-encoded the textures, I've rebuilt the app, and I've run it again, taken another trace. The performance is only a little bit better, which we kind of expected because that's what the previous offline analysis report told us, right? That we would only see a small performance increase. And recall that compared to the baseline, offline analysis told us that using BC texture compression would only give like a 7% performance increase for that draw call. And so it went from 37.3 milliseconds per frame to 35.9, which is small. But we expected that from the analysis report. Visual quality is similar. If you look really, really, really closely, you can see some absolutely tiny differences in the lighting. And this is because normal maps kind of don't like block compression, and the artifacts become more readily visible when you do the lighting. But really what we're interested in, the whole point of trying the block compressed textures in the first place, is seeing how this affects our memory bandwidth usage. Now if we run the offline analysis again, these are the new results that we get. And in this set of results, if we turned on anisotropic filtering now, we can see that it would only cost us 24% hit for this draw call. And this is compared to when we were using uncompressed texture, when this was 130% hit to performance for this draw call. So it means that now that we're using a block compressed texture, we're using less memory bandwidth, so we're not hitting the bus as hard, and so enabling anisotropic texture filtering doesn't have such a large performance hit. So in other words, we've been able to loosen this bottleneck a bit. And we can check the counters again for the anisotropic texture filtering experiment. So texture fetch stall is down to 7.7%, previously 169% with the uncompressed texture. And if we scroll down, we can see that texture memory read bandwidth is down to 8.7, 8.8 megs, previously 35 megs with the uncompressed texture. And I'm actually using DXT5 or BC3, whatever you want to call it, because I'm storing stuff in the alpha channel. Now, DXT5 has a 4:1 compression ratio, and uncompressed, this counter was showing 35 megs. Now with DXT5, it's showing 8.8 megs, and it just so happens that 8.8 megs is just about 1/4 of 35 megs. So it's nice to know that when using a texture with a 4:1 compression ratio, we're actually getting about 4:1 savings in memory bandwidth. In addition, we can also look at the baseline memory bandwidth usage. So this is with the baseline, which is using trilinear with a block compressed texture. And we can see that it's about 1.92 megabytes of texture data transferred across the bus. And remember that it cost 8.8 megs with anisotropic texture filtering turned on, which is a 4.4 times increase in memory bandwidth when we turn on anisotropic texture filtering. Yes. So remember that when we were using an uncompressed texture, turning on anisotropic texture filtering cost us 5 times the memory bandwidth. But now that we're using a compressed texture, turning on anisotropic filtering only costs us 4.4 times the memory bandwidth. And you know, this isn't that relevant to our analysis, but I just thought it was interesting that maybe as some kind of a side effect of using the block compressed textures, the GPU might be able to make better use of its texture cache to reduce that bandwidth amplification. So anyway, we've been able to confirm that we're good on the memory bandwidth front, basically. And the experiment is telling us that enabling 16 times anisotropic texture filtering is only going to have a 24% performance hit for this draw call. So what's our current status so far? Well, we want to turn on anisotropic texture filtering, but we're out of memory bandwidth. We found that we weren't using block compressed textures, so we re-encoded into DXT5 or BC3, whatever you want to call it, and we found significant savings in memory bandwidth. And now that we've reduced our memory bandwidth usage, offline analysis is telling us that turning on anisotropic texture filtering for this draw call will only cost us 24% performance for that draw call instead of the 130% or whatever it was previously when we were using an uncompressed texture. So 24% performance hit for that draw call. I think that draw call is running at like 4 milliseconds or something like that, and 24% on top of that is like an extra millisecond of cost for 16 times anisotropic filtering. I think that's fine. You know, that's an acceptable cost to us. So now, armed with that information, we can now actually just turn on AF and see how it looks. So it might be a bit hard to see the differences, or it might be impossible to see the differences from that scale, so a close-up might be in order. So the one on the left is with trilinear, the one on the right is with anisotropic texture filtering, and you can see that the one with anisotropic texture filtering is much sharper, but without any aliasing artifacts, so it looks a lot better. And the performance did go down. It went from 35.9 milliseconds per frame using trilinear to 36.7 milliseconds per frame using anisotropic texture filtering. But we expected that based on the results from the previous offline analysis, right? But it's because we were able to use offline analysis to identify that memory bandwidth bottleneck that we were able to turn on anisotropic texture filtering without our performance dropping like a rock in the first place. And you can see that 36.7 minus 35.9 is like 0.8 milliseconds of cost when turning on anisotropic texture filtering, which is about what we expected, right? And of course, we were able to figure all of this out and deduce it pretty much completely within offline analysis, right? We didn't have to do that stupid trial and error thing where we would have to make a change and then recompile it and then try it out, only to find that, oh, anisotropic texture filtering is too expensive and now performance sucks, and now I have to figure out why that is after the fact. We could just look at the report at the beginning and conclude that, oh, we're out of memory bandwidth. Oh, but we're not using texture compression. So if we used compressed textures, we could save a lot of memory bandwidth. And if we save enough memory bandwidth, we can turn on anisotropic texture filtering. And these are the results here. So it looks good now, but we're still not hitting 30 FPS. We're pretty close. We're at 36.7 milliseconds per frame, but our goal is 33 milliseconds per frame or lower, right? And again, we can just run offline analysis with our latest changes to see what else we can squeeze out of this application. So these are the results with the latest changes, and you can see that rendering the Earth is still pretty much the most expensive draw call. The other two peaks in this graph, the first one is drawing the atmosphere, and the second one is the final HDR compositing step for the post-processing, and that's somewhere off the bottom of the page. So we've dealt with the rendering of the Earth. So now let's next look at the rendering of the atmosphere. So there are actually two draw calls here, and I just happen to know that the first one is for the rendering of the inner atmosphere, and the second draw call is for the rendering of the outer atmosphere. And if you actually had this trace open in Visual Studio, you'd be able to click the link on the side, and it'll jump you into the right place into the events list, so you wouldn't have to second guess which draw call is which, but I don't have Visual Studio on hand. Anyway, we can kind of see that it's this second draw call that's the expensive one. This one takes 4.12 milliseconds, and that's kind of where we should be focusing our efforts. We come back to the common question of, why is this so slow? But the problem is that, unfortunately, all of these columns here are basically 100%, which means that offline analysis, it tried all of these things, it set point texture filtering, it halved our texture sizes and all the rest of it, it didn't find any difference at all. So we need to take a second look at the GPU hardware counters to get a sort of deeper sense of what's going on. The first thing we want to know is, where is the GPU spending all of its time? And we can see here that for these draw calls, the GPU utilization is at 96% and 98% respectively. So we know the GPU is doing stuff, but what? Luckily, Qualcomm just happens to provide a bunch of useful counters that tell us exactly that. And if we scroll down here, we can see that the percentage of time shading pixels is at 57% and 4% respectively. And the percentage of time shading vertices is 41% and 92% respectively. So that's a lot of time shading vertices, right? And we know that these two draw calls are bound by the Vertex shader now, especially the second one, which, remember, is the expensive one, and that's the one that we should be focusing our efforts on. And we can continue looking at these counters. There's the Vertex memory read bandwidth. It's nothing out of the ordinary. It's 500K is there, it's 1 meg there, it's nothing to worry about. If we scroll down again, we can see the number of vertices shaded. So 29,655 for the first draw call, and 63,241 for the second draw call. It's a fair few number of vertices, but it's not horrible, right? It comes out to a total of about 90-odd thousand vertices, which even for a phone GPU is not that bad. But take a look at the Vertex instructions. So the first draw call was 29,655 29,655 vertices, and it took 4,840,122 Vertex shader instructions. That comes out to be about 163 instructions per vertex. The second draw call was 63,241 vertices, and the GPU executed 14,839,671 shader instructions, which comes out to be about 234 instructions per vertex. And that's pretty complicated for a vertex shader. So what do we know so far about these two draw calls? Trivially, just by looking at the times per draw call, we know that drawing the atmosphere is pretty expensive. It's the most expensive singular thing in this scene. So the draw calls take a long time. We know that easily. We also know that by looking at the counters, that the GPU is spending the vast majority of its time just in the vertex shader. And we can also tell why it's slow. It's because the GPU is just executing a ton of shader instructions per vertex. And so we want to improve the performance of this. But it's kind of the easy way out is just to reduce our polygon count. So we want to find a way to improve the performance of these two draw calls, but without reducing our polygon count, if at all possible. So these vertex shaders are so complicated because what they're actually doing is solving the light scattering equations for sunlight entering the Earth's atmosphere per vertex. And these two draw calls, they're just drawing spherical meshes of the planet, right? There are two of them. There's an inner one that's close to the planet and an outer one that's a little further away. And it's just to give a sense of depth to the atmosphere. And as you might imagine, solving these sorts of light scattering equations is not cheap, and it involves a lot of numerical integration inside the vertex shader, as well as a lot of very complicated equations that I really don't understand. I must admit that when I wrote the sample application, I just implemented the formulae straight out of a copy of GPU Gems 2 without really figuring out the physics behind it. So don't ask me how Rayleigh scattering works, because I'm not a physicist. But of course, really all of the trouble and consternation from this enormous vertex shader is just to produce a color value at the end of it. And this color value gets interpolated in the normal manner and gets fed into a pixel shader that literally looks like this. Now, because I don't really have a PhD in atmospheric optics, I don't think I can optimize the scattering equations themselves. But there are things that we can do as clever graphics engineers. We know that because this is a sphere, exactly half of the polygons will be culled due to backface culling. And this is kind of trivial to prove because it's a sphere. Exactly half of it will be facing away from you at all times. So that means that we're calculating all of these lighting equations to generate a color value for vertices that are going to get culled anyway. You're never going to see them. For vertices on triangles that are on the backside of the planet relative to the camera, we only need to output the position for those vertices. We don't need the color value. So we can implement a sort of poor man's backface culling, right? And we can do that inside the vertex shader and use dynamic branching inside the vertex shader to skip the complex lighting calculations for vertices that don't need them. And it turns out it's really easy to implement because we know the position of the center of the planet, we know the position of the vertex to shade, and we know the position of the camera. If we take a vector from the center of the planet to the camera, and we take a vector from the center of the planet to the vertex, and we take the dot product of these two vectors, and remember, the dot product gives us the cosine of the angle between the two vectors. If this dot product is negative, then we know that the vertex is necessarily on the other side of the planet, right? That it is not visible by the camera, and therefore we don't need to perform these complex lighting equations. And so that's what it looks like. It's nothing fancy. It's very simple. Luckily, Windows phones are all feature level 9.3 parts, which do support dynamic branching in shaders. Now, having a dynamic branch in a shader is usually not great for performance, but in theory, if we can cut down on the number of vertices that need these expensive lighting equations, it might balance out the cost of the dynamic branch in the first place. So, what's our current status? We were able to use offline analysis to identify where the workload was, and we found that it was just completely vertex bound for the atmospheric draw calls. And that the reason for this is just because the GPU was doing way too much work on the vertex shader. And now we can apply our optimization and see how that changes the results. So I've made the change. These are the results. And yes, after making the change, the frame time has decreased from 36.7 milliseconds per frame to 30.5 milliseconds per frame. And the scene looks exactly the same because the vertices where we skipped the lighting equations were on the backside of the planet anyway. And so they were being culled. And our frame time is now below 33 milliseconds. We've reached our goal of 30 frames per second. And in case you want to be really paranoid and really want to double check that your dynamic branch in your shader is actually working, you can run offline analysis again. And you can see right away the graph at the top, the time taken for this draw call for the outer atmosphere, it's dropped significantly, right? So that's without the dynamic, that's with the dynamic branch, without with. And you can see that bar has gotten a lot shorter. Obviously, it got a lot faster. So if we take a second look at the counters, we can see that the Vertex instructions for this draw call has dropped from 14.8 million, which is what it was before, to only 5.7 million. So it did actually work. So we've reached our target. We're happily running at 30 FPS. That means we're done, right? Wrong. So this is a device which we call the QID. You might have seen Joe Belfiore with one on stage at Mobile World Congress this year. And this device is more similar to the types of devices that will actually be shipping in volume to customers around the world. So far, we've been running on a Qualcomm Snapdragon 800 silicon on a chip, and that's what's in this engineering device. And it's the most powerful chipset that we currently ship Windows phones on. I think it's got a quad-core Crate CPU in it with a 450 megahertz Adreno graphics processor and all the rest of it. I think the Lumia 1520 has got a 8974 chipset in it. But really, the bulk of the devices that we'll be shipping, most of the phones that people buy, are going to be more like this, more like the QID. And this QID has a Snapdragon 400 in it, which is somewhat less powerful and lower power consumption than what we've been using so far. So we want our application to run well on the QID as well. So we can take our application, we can deploy it to the QID, and it's slower. It runs, and that's always a good sign, but it's going at a third of the speed of the 8974. 100 milliseconds per frame is about 10 frames per second, which is not great. So we can repeat the exercise, right? We can take our existing trace and we just run analysis on the QID on this device here. But there's not a whole lot here. Most of the columns that you can see are sitting happily at 100%, meaning that there's no change. There's a little bit of green in this column here, in the 16-bit pixel render target format column, and that's kind of situational. It depends on your application whether you want to use a 16-bit color depth. Realistically, it's not something that we want to change for this application because we're currently rendering to a 64-bit per pixel floating point render target, and we need that for the high dynamic range and the post-processing and all the rest of it, and we kind of don't want to sacrifice that. The only other place where we can see gains are in the 1x1 viewport size experiment. And what this means is that with a 1x1 viewport size, there are no pixels to shade, right? So we keep the vertex load, but there are no pixels. And we can see that for a lot of these draw calls, having no pixel to shade makes a huge difference in performance, right? This tells us that we're likely to be full rate bound. So for example, this draw call, the one that took 20 milliseconds on its own, drawing the Earth, that got 25 times faster when there were no pixels to shade. And obviously the post-processing, because that's nothing but pixel workload, this one got approaching infinity times faster for that particular draw call. And we can confirm that we're full rate bound by taking a double look at the GPU counters. So if we scroll down and have a look, we can see that for this draw call, drawing the Earth, which is the single most expensive draw call, which is the Earth, we're spending 99.75% of the time shading pixels. And it's not the most trivial shader either. 208 ALU operations per pixel. And it's kind of the same deal with all of the HDR post-processing. It's spending almost 100% of the time shading in the pixel shader. So it's like 99.9993% of the time inside the pixel shader. And so the reason we're so heavily fill rate bound is that we're trying to run at the same 1280 by 720 resolution that the 8974 chipset was, except that this GPU has much, much less shading power. So we're bound by fill rate. Well, it's kind of the easy way out is just to reduce your resolution. It's kind of the easy way out, yes, but we're running on a device which has a much less powerful GPU, but we're trying to keep it at the same resolution, which just isn't going to work. So if we render at 2/3 the width and the height on the back buffer, we end up having to shade about 56% fewer pixels. And 1280 by 720, 2/3 both ways, that ends up being about 850 by 480. And our performance has increased from 102 milliseconds per frame to 52 milliseconds per frame, which is about double the performance in exchange for shading a little bit less than half the number of pixels. And the reduced resolution looks okay. It's probably a little hard to see the difference from the static image, and it's running at 20 FPS. Is there anything else that we can do? Well, yes, of course. There are always things that we can do to improve the performance. We could continue looking at the data and continue trying to find places for improvement, but I kind of didn't want to turn this into a 2-hour presentation, so I think I decided to just stop there, and even though we're only running at 20 FPS. So what have we been able to achieve so far? What's the summary? Well, first we just corrected a rookie mistake of turning on mip mapping to fix visual artifacting, right? we found that when we did that, there was a hit to visual quality. And we wanted to enable anisotropic texture filtering to increase the image quality again. But even before enabling and trying AF, we could see that in the analysis report, it would have an extremely heavy cost that we just couldn't afford. We were able to use GPU counters in offline analysis to conclude that we were just being severely limited by the 8974's memory bandwidth. And we also deduced from the report that we weren't currently using block compressed textures for the draw call, which was just blowing out the memory bus. And after we re-encoded our textures to BC3 or DXT5, we were then able to use offline analysis to determine that the cost of anisotropic texture filtering was more acceptable. And we were then able to turn on 16 times anisotropic texture filtering as we wanted in order to increase our visual quality. So to finally hit the target of 30 FPS on the 8974 chip, we used the analysis report to identify that the atmospheric rendering was a particular hotspot in our application. And we were able to discover that the performance of the atmospheric rendering was just completely bound by the Vertex pipeline. And we found that it was being caused by a Vertex shader that was just too complex rather than some other random part of the GPU pipeline. So after applying our optimizations to the atmospheric Vertex shader, we were able to hit our 30 FPS target on the 8974, but performance was still too low on the 8226, which is the QRD over here. We found that via the one-by-one viewport experiment, the QRD was just bound completely by fill rate because it was trying to run at the same resolution as the 8974, but with a vastly less powerful GPU. So to compensate for that, we just took the simple and easy way out and just reduced the resolution. This brought our frame rate up to 20 FPS, which is still lower than our target, but there's undoubtedly more stuff that we could do to improve the performance of the QRD, but I think I'll stop here. So where can we actually find offline analysis? It'll be available in Visual Studio 2013 Update 2, so when you get the update, you can try out Graphics Frame Analysis, which is its official name. Because this is going into a release, an update release, as opposed to a fully fledged VS release, there's a lot of stuff we wanted to do, but we just didn't have time to fit into the release. So any feedback that we get is always valuable from real-world usage, and it helps us to prioritize what we should be working on next. So for all the developers out there, next time you need to profile the rendering of your application, be sure to give offline analysis a try. I think that's all I had.
Adrian, thank you so much for your presentation. Like, you know, people out there like me who kind of know what graphics might be about but have, you know, zero experience in it. I really appreciate how, you know, you're able to just talk about things in broad terms of, you know, compression, about rendering, about resolution, and of course about quality. And so that was really fantastic.
Yes, I tried to keep it as accessible as I could because I know that this topic area can be a little bit obtuse at times. So it's good to know that that you enjoyed it.
Yeah, I think you left out just the right amount of detail and you put in just the right amount. So thank you so much, and for you guys out there, hope you enjoyed.
Thank you.
Hey, this was great. I really liked it. You know, a lot of details. And now I remember, you know, they work very close together. You know, the OSG team and the Visual Studio debugging, graphics debugging team in Visual C++ to deliver this feature. And indeed, is integrated in the Visual Studio debugging framework.
Very nice.
The PICs, you know, what we call it internally. And it's going to come up in Spring Update for VS 2013. That's great. You know,
look forward to
great collaboration. More of that coming, of course. These guys are always working together. A lot of IEM sessions across the buildings.
And so
that's great.
Yeah, speaking of optimizing things on phone, I heard you got
I got a new phone. I got a new phone. I got a beautiful phone that is like a lighter.
Yeah, it's like,
of course, it's a Windows phone.
Click that and a little flame comes up.
Yes, it's a new model. You can't
the
have
Windows
this.
line.
Yes.
Lights things for you.
It's not. My wife broke my phone, and so I had to get a new phone, an older phone. Whatever. Anyway, so, you know, do you have also something ready for next?
Yeah, so next episode we're going to respond to Nika159's request of how to use the final keyword to take advantage of it for devirtualization, for some optimization. So you guys can look forward to that, and feel free to take his lead. You know, if you want to see something, put it in the comments, and we'll do our best to make it happen.
More debugging, more graphics, more C++, more whatever.
Anything
let us know.
Yep.
Native, of course.
Has to be native.
Has to be native. Okay, cool. Thanks.
Thank you guys.
Bye-bye.
Bye.